Hi, in this video we're going to have a look at node voltage analysis of circuits. So you know that Ohm's law is written as the potential difference is equal to the current multiplied by the resistance R. And this can also be written as I equal to the potential difference divided by the resistance. So you should know the Kirchhoff's current law, KCL, also, which is a sum of current in is equal to sum of current out. And also the Kirchhoff's voltage law, which is sum of potential difference across a closed path will give you 0. Okay, so these laws are applicable when solving questions in node voltage analysis. So for example, if we have a potential over here, let's call it V2, and here we have a resistance, let's call this one R1, and let's call this potential over here as V1. So if a current will flow across the resistance from V2 to V1, it means that V2 is at a higher potential than V1, because current will always flow from a positive to a negative terminal. So positive meaning that it has a greater potential, and negative meaning that it has a low potential. So this one is high, this one is low. So current will flow, let's call it I1. So I1 will flow from a high to a low potential. So by Ohm's law, we can write I1 as the potential drop. So it is a potential difference, the difference between the two potential, V2 minus V1, the high minus the low, divided by the resistance, which is R1. Okay, we apply this law, the Ohm's law, so which is R1. So we can write the current I1 as V2 minus V1 divided by R1. Okay, this will be applicable in node voltage analysis. Let's see an example on how we can use node voltage analysis to solve problems. So the first example, using node voltage method, find the current in the 3 ohm resistor. So we have a current I in the 3 ohm, so we have to find this current I. And this is 4 volt and this is 2 volt. Okay, so first of all we have to assign a reference node. So the reference node would be at 0 potential. So it is a node which would give the circuit, every branch of a circuit is 0 potential, and this node could be assigned over here. So we have to put the reference node. So reference node is at 0 volt. So everything in the branch over here to this branch is at 0 potential. So these are at 0 potential. Okay, these are at 0 potential. So meaning that all the current would flow towards the 0 potential. So we have a source over here, 4 volt. We have a 2 ohm resistors and 3 ohm resistors. We have another 2 volt. So here we don't know the voltage. So let's call this one V1, the voltage V1. And here we have 4 volt, another source. So let's assign current in in the circuits. So you know that I1 is flowing over here. So I1 would flow in this direction. So this is I. So now I1, let's assign this current as I1. Okay, flowing from the positive source to the node V1. And therefore, in this branch, the current would flow toward the reference node because it is at zero potential. Current always flow from high potential to low potential. So let's assign this I2. Okay, now we have assigned our currents and voltage. So our potential, which is at this node, node 1, we have assigned it as voltage V1. So now let's apply KCL at node 1. So at node 1, okay, the potential is at V1. So if we apply the current law, it is the sum of current in is equal to the sum of current out. Okay, so the current entering the junction, so the node at V1 is I plus I1. So I1 is entering and I is entering. So the current leaving the node is I2. So the current out is I2. So now you can convert I into Ohm's law in terms of V, the potential difference, and R. So the current I, so you know it is flowing toward V1. So V1 must be lower potential. So the higher potential would be the 4 volt and the 2 volt. So the source are added because this is negative, this is positive, this is negative and positive. It is in the same direction. And therefore, the voltage would be 4 plus 2 minus the lower potential, which is at V1, divided by the resistance. So I is flowing in 2 ohm and in 3 ohm. The total is a series which is 2 plus 3, 5 ohm. Okay, and I1, the current is flowing from 4 volt to V1. So V1 is at a lower potential. Therefore, it would be 4 minus V1 divided by the resistance 2. And this is equal to I2. So I2 is in this direction towards the reference node, and V1 is at a higher potential. Therefore, it would be V1 minus the potential over here is 0. So minus 0 divided by 2. So now we have an equation in V1. We can solve for V1. Okay, this would give 6 minus V1 divided by 5 plus 4 minus V1 divided by 2 is equal to V1 divided by 2. And we can simplify this. So 6 over 5 minus V1 over 5 plus 4 over 2 minus V1 over 2. And this we can send it to the other side is minus V1 over 2. And the right hand side is 0. Okay. Now, so we can solve for like terms like V1. So it is minus 1 over 5 minus half times the V1 plus 6 over 5 plus 4 over 2, which is 0. Okay, so this would give you a minus 1.2 times V1 plus 3.2, and this will give you 0. And therefore, you can find V1 is equal to 3.2 divided by 1.2, you'll get 2.6 volt. V1 is 2.6 volt. Okay, this potential is 2.6 volt. Let's write it as 2.6 volt. Now, to find the current I, we know the equation. Okay, so I is written in Ohm's law as, so 4.4 plus 2, 4 plus 2 minus V1 divided by 5. So this was in terms of Ohm's law. And V1 we already know. So it is 6 minus 2.6 divided by 5. So when you calculate this, you will get a value of 0.68 ampere. So the unit for current. So this is the answer. A simple example on how to use node voltage analysis to find a current. Let's see another example on node voltage analysis. So write the node voltage equation and determine the currents in each branch for the network given. So first of all, let's assign the reference node, which would be here. Okay, and let's assign the current. So this is I1 flowing here from the source, from the current source flowing into this node. Let's call this node 1, and this node, let's call it 2. So let's call this one I2 flowing toward the reference node, and this is I3. Okay, let's call it I3. So here is 2, the node 2. So the current will flow into node 2 from the voltage source. So let's call this I4 and I5. So I4 is directed towards a reference node. So let's call this one the potential V1 and this one the potential V2. So after we assign everything over here, now we have to apply the KCL at node 1. So KCL state that the sum of current in must be equal to the sum of current out. So the current entering at 1 is I1 plus I3. This is equal to I2. So I1 is 5 ampere from the current source. So it is 5 plus I3 is V2 minus V1 divided by the resistance 3. And I2 is V1 minus 0 divided by 10, the resistance. So to simplify this, so it is 5 plus V2 over 3 minus V1 over 3. This is equal to V1 over 10. So we can actually put this to the other side. So it would be minus V1 over 10. So let's call it minus V1 over 10, and this is equal to 0. Okay, so we can multiply everything by 30. Okay, so here you will have 150 plus 10 V2 minus 10 V1 minus 3 V1, and this gives you 0. So simplifying the terms, so we have V1 and V1 here. So this will give you 10 V2 minus 13 V1. Okay, and this is equal to, let's call it as V1 and V2. So minus 13 V1 plus 10 V2, and this is equal to minus 150. So this is equation 1. Okay, now let's apply KCL at node 2. So if we apply KCL at node 2, so the sum of current entering is equal to the sum of current out. So sum of current in is I5, okay, only I5. And sum of current out is I3 and I4. Here. So I5 is 10 volt minus V2. 10 minus V2 divided by 1 ohm resistance. I3 is, okay, V2 minus V1 divided by 3. And I4 is V2 minus 0 divided by 5. So now let's multiply all equation by 15 to eliminate the denominator. So here we'll have 15 times 10 minus V2 is equal to 5 times V2 minus V1 plus 3 times V2. So we have eliminated the denominator, and now we can simplify the equation. So 150 minus 15 V2, 5 V2 minus 5 V1 plus 3 V2. Again, here we have V2 and V2 over here. And we have 15 V2 in this other side. So altogether we'll have 8 plus 15, which is 23 V2 minus 5 V1, and this is equal to 150. So we can write it as minus 5 V1 plus 23 V2 is equal to 150. So this is equation 2. So now we have equation 1. Let's write it over here. And equation 2. So you can use simultaneous equation, or you can use Cramer's rule to calculate for the voltage V1 and V2. Okay, so let's use simultaneous equation. So you'll have from this side V2 is equal to 150 minus plus 5V1 divided by 23. So this is equation 3. You have to replace 3 in equation 1. Okay, we have minus 13 V1 plus 10 times V2 is 150 plus 5 V1 divided by 23, and this is equal to minus 150. So you can solve for V1. So if you solve for V1, you will have your answer. V1 is equal to 19.87 volt. And if you replace it in the other equation, you will have V2 is equal to 10.84 volt. So you can solve this to find V1 and V2. So now in the question we are asked to find the current in all the branch. So we have to find I1, I2, I3, I4, I5. So all the current. So I1 is already given. It is 5 amps. And I2, so I2 is V1 minus 0 divided by 10. So we can write it V1 minus 0 divided by 10. So V1 is 19.87 divided by 10. So this will give you 1.987 amps. Okay, so I3 would be V2 minus V1 divided by 3. So V2 minus V1 over 3. So which is 10.84 minus 19.87 divided by 3. So this would give you a value of minus 3.01 amps. So you can check your answer. So I4 would be V2 minus 0 over 5. So this is I4. V2 minus 0 over 5, which is 10.84 divided by 5. And this will give you 2.168 amps. And I5 is 10 minus V2 divided by 1 ohm resistance. So 10 minus V2 over 1, which is 10 minus 10.84 divided by 1, which will give you a value of minus 0.84 amps. So these are all the currents in all the branches in the circuit. So these are the answers.